these problems are called initial value problems because we're given an initial value of the problem. We have a derivative of the function g. We need to find the function, the original function g, who satisfies this, what we call initial condition or boundary. That says that when we put -1 into the function g, we should get back 1, right? That's what it means if it goes through that point. So first let's investigate how to even find the function g. Now we have g's derivative, so we need to think backward about our differentiation rules. For example, this 1 over x squared, you could think of that as x to the -2. And then you say, gee, what did I differentiate to get -2 as an exponent? Well, if I take x to the -1 and differentiate it, I would take away 1 from that exponent and get to -2. So that sounds like a good starting point. However, if I were to differentiate down here, let me just sketch out my first derivative. The derivative of x to the -1 is -x to the -2, and that's not what I have here. I have positive, so I don't want positive. If I put the negative in the original function, then when I differentiate, I have -1 times negative makes positive x to the -2, and that matches that first term, so I feel good about that. Now let's look at the second term, plus 2x. What function did we differentiate to get 2x? The derivative of x is 1, the derivative of x squared is 2x, so let's use that one. If we differentiate x squared, we get 2x, so we match again. Now remember, these are families of functions. There could be some constant out there in this function, so we need to allow for its presence and get rid of that derivative. So now I think I'm pretty confident that we have a function g whose derivative is the one that's given, right? We have a given derivative and we found the function. Now though, we want to invoke the initial condition. We want to find the value of c that satisfies that initial condition. This first thing right here, g of x with the plus c, is called a general solution to a differential equation. We would like to find a particular solution, namely the one that satisfies this initial condition. So let's invoke the initial condition or apply the boundaries to solve for c. G of -1 equals 1. And I know that g of x is -x to the -1 plus x squared plus c. So we're going to combine these. These are a system. That gives us that g of -1 is -1 to the -1, make that substitution, plus -1 squared plus some c value. I want to find c. And when I plug in -1 into this function, I better get back 1. So you see how I merge these two guys? I use this value for x, and x, and x. And I realize that once I make that substitution, it should all equal 1 when I'm done. So that's how we got this equals 1. So let's work with these last two sides of the equation. -1 to the -1. That's -1 over -1, right? Plus -1 squared is just 1, plus c equals 1. Now -1 over -1 is 1, so we have 1 plus 1 plus c equals 1, so 2 plus c equals 1, so c must equal -1. Now that I found the value for c, we can substitute that back into the general solution. Remember we had this thing, g of x was negative x to the minus 1 plus x squared plus some value c, but I now know c. So if we plug him in there, we get this thing called a particular solution, a specific solution for this initial condition or boundary. That means we found the function, right? We found the function from his derivative, and we made sure that that function passed through this point, the initial condition. That's called a particular solution. Let's do it again. All right, we want to find a function who has the given derivative and passes through the point 0, 0. So first let's work on the function. If the derivative is secant tangent, what function did we differentiate to get secant tangent? Must be something trigonometric. Maybe you run through them in your head and arrive at secant. The derivative of secant is in fact secant tangent. Then we need something that when we differentiate it we get 1. That must be just the variable because the derivative of t is 1. And there is this constant factor that we add in there. Take care of any miscellaneous bits, right? So this thing right here is called, remember, the general solution. We use the boundary, the fact that this curve, r, must go through the point 0, 0. When you substitute 0 for t, you will get back 0 as the y value or as the r value. So let's invoke the initial condition or apply the boundary to solve for c. The boundary says that when r is 0, t is 0. So 0 equals the secant of 0 minus 0 plus c. Well, the secant of 0 is 1 over the cosine of 0, which is 1. Minus 0, I can handle that. Just 0 plus c. So c must be negative 1. Once we have c, we can substitute it back into the general solution and get the particular solution. The particular solution is the function r that has the given derivative and passes through that point is none other than the secant of t minus 1. If you don't believe it, you could verify that it does in fact go through this point and then differentiate it to make sure that it really does have that derivative.